Hello everyone and welcome. My name is Tobias Handirk. I'm a PhD student at the University of Wuppertal, and I'm going to present our work Forward Secure Zero RTT Goes Live, Implementation and Performance Analysis in QUIC. This is joint work together with Drees, Gellert and Tibor Jager from the University of Wuppertal, as well as Fynn Dallmeier, Jonas, Klauke, Nachtigall, Timo, Renzelmann and Rudi from Paderborn University. As the title suggests, we implemented a zero-RTT key exchange protocol and analyzed its performance in comparison to QUIC. But before presenting the implemented protocol and the performance analysis, I first need to introduce some basic groundwork. So I want to start with a discussion on latency in key exchange. When two parties, for example a client and a server, want to communicate encrypted, the communication partners need to establish a session key. So let's see how this process to establish the session key looks like in practice on a high level. The first step is that the communication parties establish a reliable channel. A reliable channel ensures that no messages are lost, that the messages are delivered in the correct order and to the correct destination. The most used protocol in practice for this is TCP. When using TCP, the communication partners execute the TCP through a handshake, which takes one round-trip time. After establishing the reliable channel, the communication parties proceed to execute the key exchange. The most used protocol for this in practice is TLS, and its two most prominent versions 1.2 and 1.3. The key exchange of version 1.2 takes 2 round-trip times, which was then improved in version 1.3 to only 1 round-trip time. So we see, depending on the TLS version, it takes 2 or 3 round-trip times before the first application data can be sent. But why is it even important how long it takes until the first application data can be sent? Well, first of all, if we have a low latency, this saves time and resources. And a low latency improves the user experience. This is most important in rural networks where we have a slow connection anyways, and therefore every extra message exchanged before the first application data carries an extra weight. Additionally, a low latency is also interesting from a business perspective. In 2006, Amazon found that delaying their web page on purpose by 100 milliseconds led to a reduction in sales by 1%. In 2017, Akamai and Google observed similar results and found that a higher delay until the web page is loaded led to a significantly increased probability of users abandoning the connection. So now, of course, the natural question is, can the latency be improved even further? So we had the two phases to establish the secure channel. First, the establishment of a reliable channel with the TCP through a handshake, and then the key exchange with, in this case, TLS. And in both phases, it is possible to reduce the number of round-trip times. First, we can use UDP instead of TCP as the transport protocol. UDP does not need a through a handshake like TCP and therefore saves 1 round-trip time. However, UDP by itself does not establish a reliable channel, so we would need to implement some extra functionality on top of UDP to ensure some TCP-like reliability. Then in the second phase, we can do a zero-RTT key exchange, where the client can send application data in its first flight of messages. Therefore, the client can immediately send encrypted application data without waiting for a response from a server. The first zero-RTT key exchange protocol was QUIC, which was developed by Google in 2014. QUIC does build on top of UDP and does implement some TCP-like reliability. TLS 1.3 also offers a zero-RTT mode, but only for session resumptions, where the communication partners reuse the cryptographic state from a previous session. In this talk, I want to focus on QUIC, so let's see how that protocol works. In QUIC, the very first connection between a client and a server still always requires a 1 RTT handshake. To start the 1 RTT handshake, the client basically sends an empty hello message to the server. The server then replies with the so-called server configuration, which is essentially a medium-lived DB share with a typical lifetime of 2 days. Moreover, the server configuration is signed with the server's long-term secret key. After verifying the signature, the client generates its own Diffie-Hellman share, and derives an initial session key from the common defilement secret G to the SX. The client can use this initial key to encrypt some application data and send them to the server together with the defilement share G to the X. Now the server can compute the same session key and decrypt the application data. Afterwards, the server generates a fresh defilement share G to the Y, sends it to the client, and both parties derive a second, stronger session key from G to the XY. From then on, only the second key is used for the communication between the two parties. On any subsequent connection, the client reuses the defilement share from the server configuration and is immediately able to send its own defilement share to the server. If the server configuration expired, the parties again execute a 1 RTT handshake, where the client then receives a fresh server configuration. So now we have seen how QUIC enables a 0 RTT key exchange, but there are two drawbacks from a security standpoint. The first drawback is forward security. Forward security means that any communication between two parties remains secure, even if one of them is compromised at some later point in time. So let's envision a scenario where an adversary records all communication between a client and a server. If the adversary then, at some later point in time, obtains the secret exponent of the defilement share in the server configuration, it can derive the same initial session key and retroactively decrypt the message encrypted under the initial key. Thus, the payload encrypted under the initial session key is only forward secure after the server configuration expired and the server discarded the secret exponent. The second drawback is replay protection, meaning that requests by a client are executed only once by a server, even if that same request was received multiple times. In QUIC, an adversary can simply resend the message encrypted under the initial session key, and the server cannot notice that the message was replayed, and therefore will process the data again. Now, I want to note that these drawbacks exist not only in QUIC, but also in the 0 RTT mode of TLS as well. That 0 RTT mode works similarly in that the communication parties first derive an initial session key, and after exchanging some messages, derive a second session key. And there again, the message encrypted under the initial key is neither forward secure nor replay protected. Now, in recent years, it was discovered that key exchange protocols can be improved even further to achieve forward security and replay protection for all messages by utilizing a new cryptographic primitive called punctuable key encapsulation mechanisms, or short PKEMs. Punctuable encryption was first introduced by Green and Myers in 2015 to achieve forward security in asynchronous messaging. To achieve forward security in key exchange, we do not use punctuable encryption, but PKEMs. As the name suggests, PKEMs are a special form of conventional KEMs. In a conventional KEM, we have the algorithms keygen, NCAP, and DCAP, where keygen outputs a key pair consisting of a public and a secret key. NCAP takes a public key and outputs a symmetric key and a ciphertext, and DCAP takes a secret key and a ciphertext and outputs a symmetric key. In a PKEM, we have an additional algorithm called punc. The algorithm punc takes as input a secret key sk and a ciphertext and outputs a modified secret key sk prime. This modified secret key sk prime then has the special property that it can be used to decapsulate all ciphertext except the one for which punc has been called. In this way, we can ensure that ciphertext can be decapsulated only once. And by repeatedly calling the punc algorithm for different ciphertexts, we can gradually revoke decapsulation capabilities of the secret key. Now we can use a PKEM to construct a 0 RTT key exchange protocol. This construction was developed by Günther et al. In 2017. At the start of the protocol, of course, the server generates a key pair. Then, to actually execute the key exchange, the client calls the NCAP algorithm. It may then use the generated symmetric key to encrypt application data and send them to the server together with the generated ciphertext. Upon receiving the ciphertext, the server decapsulates it to obtain the symmetric key and is able to decrypt the application data. Additionally, the server calls the punc algorithm and updates its secret key with the secret key sk prime resulting from the call to punc. So now let's imagine that an adversary compromises a server and obtains its secret key. Since the server always updated its secret key with the punk algorithm, the adversary is unable to decrypt any server text it may have recorded previously. Moreover, if an adversary replays a message, the server is unable to decapsulate the server text and thus cannot process the request a second time. Therefore, this construction achieves forward security and replay protection. Now, PCAMs sound like a great solution. However, there is a big downside, namely that all known constructions require very expensive cryptographic operations like bilinear pairings in comparison to the Diffie-Hellman operations in QUIC or TLS 1.3. Therefore, discussing latency in key exchange until now may have looked like this. So I spent lots of time telling you how important it is to reduce the latency in key exchange, and now suggesting a protocol which is computationally very expensive just does not make sense, even if we achieve a little bit more security, right? Therefore, the question in our work was, how much worse is it actually? Or is it maybe feasible to trade off a little bit more latency for better security guarantees? To answer this question, we integrated the zero-RTT key exchange protocol based on PCAMs into the Chromium web browser to compare its performance to QUIC, which is already implemented in Chromium. Now, before going into the details of our results, I first want to talk about the specific PCAM scheme that we implemented. The scheme we implemented is called Bloom filter cams, or short BF-cams, and was introduced in 2018 by Dallmeier et al. BF-cams are a very efficient form of PCAMs. However, this comes at the cost of a non-negligible correctness error and a very large secret key. In a BF-cam, it can happen with non-negligible probability that the decap algorithm fails for some ciphertext, even though punk has never been called for that ciphertext. This fail probability starts out at 0 for a freshly generated key and then increases exponentially with each call to the punk algorithm. How fast the probability grows additionally depends on two parameters chosen during key generation. So when generating a key pair, we can choose an upper bound for the failure probability and then set up the BF-cam such that the chosen bound is guaranteed to hold for some chosen number of punctures. If punk is called more often than the chosen number, there are no guarantees anymore on the failure probability. In that case, the key is kind of exhausted and the server should generate a new key pair. Nevertheless, since the failure probability grows exponentially in the number of punctures, it will remain at negligible values for a very long time. Now, the two parameters chosen at key generation not only influence the failure probability, but also the size of the secret key. So when generating a key pair, we have a trade-off between the size of the secret key and the failure probability. Choosing a lower bound on the failure probability or a higher maximum number of punctures leads to a larger secret key size. We implemented this BF-cam scheme and the zero-RTT key exchange protocol presented earlier in the Chromium web browser. We implemented it alongside QUIC, utilizing UDP, and we used the TCP-like reliability features of QUIC. We did not change any functionality of QUIC, which allows us to benchmark both protocols. We published our implementation on GitLab, and you can find the link to our repository here on the slides and in our paper. So now we can finally get to our performance analysis. In our benchmarks, we considered a scenario where several clients connect to a single web server multiple times. In our setup, we used one computer as the server and two computers as the clients. The computers were connected via gigabit Ethernet, and we did not use any latency emulation in the network. Since the machines are in close physical proximity, this leads to a almost negligible network latency, which allows us to measure only the performance of the key exchange protocols. The Chromium source code comes with test applications for clients and servers, which we use in our benchmarks. On each client machine, we ran 2 client applications and thus had a total of 4 client applications connecting to the server. The client applications repeatedly send HTTP requests to the server, requesting a small file of 100 bytes size. This again allows us to measure only the performance of the key exchange protocols, since the time to transmit 100 bytes is negligible. The client is disconnected after each request, such that for each request a new key exchange is executed. Although we have a fixed number of client applications running, we are able to simulate different loads on the server by varying the time that clients wait between sending requests. We varied this waiting time from 1 second between each request to no waiting time. So let's get to the results of our benchmarks. The most important metric for us was the throughput on the server side, meaning how many requests can the server process per second. To be more precise, we are not interested in the absolute numbers, but in the numbers in comparison to QUIC. To measure the throughput, we let the client applications run for 30 seconds with each handshake protocol and different waiting times, counted the number of requests successfully processed by the server, and computed the average per second. The results can be seen here in this graphic. On the x-axis, we have the waiting time between requests for the clients, which in essence is the offered load to the server, and on the y-axis, we have the server throughput. You can see that for a small offered load, all requests can be served without delay, and the throughput is nearly identical to the offered load. As the load increases, the server exhausts its computational resources and reaches the throughput limit. Using our implementation, the server maxes out at a throughput of 34 requests per second, while using QUIC, the server can process roughly 260 requests per second. Due to the more expensive computations in our implementation, the server reaches its throughput at a lower load in comparison to QUIC. From the observed values, we can see that the ratio of the maximum throughput between QUIC and our implementation is roughly 8. Moreover, we measured the number of CPU instructions per request on the server, where we again observed a similar ratio of roughly 8, and we can clearly see a correlation between the CPU instructions per request and the maximum throughput. A second important metric we measured is the memory usage on the server. As mentioned before, a BFCAM requires a big secret key, where the size of the secret key depends on the parameters chosen at key generation. To recall, these two parameters are the upper bound on the failure probability and the maximum number of punctures. Now here I want to give one example of the memory usage for a varying maximum number of punctures with a fixed bound on the failure probability. First, in red, we see for comparison the memory usage of QUIC, which lies at about 15 to 20 megabytes. Then in blue, we have the measured memory usage of our implementation for the failure probability bound fixed to 10 to the minus 3 and different maximum number of punctures ranging from 1 to 200,000. As we increase the number of punctures, we can clearly see that the memory usage scales linearly with the maximum number of punctures and reaches to about 750 megabytes for 200,000 punctures. If we fix the maximum number of punctures and instead vary the failure probability bound, the memory consumption would grow logarithmically in the failure probability bound. Another metric we measured is the duration of the full handshake, which of course correlates to the maximum throughput. And we measured roughly 4 milliseconds for QUIC and roughly 36 milliseconds for our implementation. Now again, I want to stress that this measurement includes only a negligible network latency. In a real-world scenario with the added network latency, this ratio would be smaller than 8. If, for example, we consider a network latency of roughly 15 milliseconds, the ratio would be decreased to only about 1.5. In rural networks, where the network latency may be 50 milliseconds or even higher, our implementation would even outperform QUIC due to saving one round-trip time. When looking at the size of the messages exchanged during the handshake, we see only a small difference. Our implementation saves 170 bytes compared to QUIC, since we are able to shave off some values like the service diffie and share. Now it's important to note that the size of the ciphertext from the BFCAM scheme depends on the failure probability bound, and this was measured for the bound set to 10 to the minus 3. The size of the ciphertext from the BFCAM grows logarithmically in the failure probability bound and would vary only by at most a few hundred bytes. Additionally, although in theory the sizes differ, we were not able to observe the differences on the wire when expecting the messages with Wireshark. This is due to the messages being padded to the full MTU size on the network layer, which then cancels out the small size differences. Okay, this brings me to the end of my talk. So to give a quick summary, we implemented a forward-secure zero-RTT key exchange protocol based on PCAMs, which, in contrast to QUIC and TLS, provides forward security and replay protection for all messages. The main drawback of the construction is the increased computational load, which, in our experience, was increased by a factor of 8 in comparison to QUIC. Additionally, the memory consumption is significantly increased and easily reaches a few hundred megabytes or even more, depending on the failure probability bound and the maximum number of punctures. The measurements show that zero-RTT key exchange from PCAMs can be considered practical, and with a high network latency is even more efficient than QUIC. Since PCAMs are a relatively novel area of research, we hope that in the future more efficient constructions may be developed, which may be able to mitigate some of the drawbacks of the BFCAM scheme that we implemented. Any improvement in the PCAM scheme would directly translate to improvements in the key exchange protocol. Okay, so thank you for your attention, and if you have any questions, please do not hesitate to contact me or one of my co-authors.